Since nobody seems to really need the AI summary, I'm not going to be using it anymore. I guess people are okay with whatever they get to watch in the recording. Okay, so let's first start off with just a review. So your due date for assignment number 2 is, I'm going to actually accept them all the way to the 9th of June. So let me go ahead and go in and make sure that that is the case. So let me just update that, give you guys a few more days in case I haven't already done that. How many of you have completed assignment number 2? Because the later part of today's class is for you to complete assignment number 2. So if you've already completed it at that point, you're free to, you can still stick around or you can take off. So let me just go in here. I see there's about 14 submissions for assignment number 2. So a lot of people have already completed that. So that's pretty good. Let me update that. Add a couple of days to give you guys more time. More time to finish. Okay. All right. That covers that. That's assignment number 2. Then what we have is next week. So next week, we will have test number 1. At some point today, we'll talk about test number 1 a little more as well. I'll review a couple of things, maybe mention a few hints as well for test number 1. And then in 2 weeks, which will be the last week that I'm with you, it'll be assignment number 3 that you'll have until the 24th to submit. After that, the course will be taken over by a different professor. I'm hoping that he or she, I'm not sure who it is, but I'm hoping that this person will come and visit you during the final week that I'm with you, so that you can ask any questions and see what this person has to say about their takeover. Okay. All right. So let's take a look at the slides. So much of what we'll work on today is we'll review some more vector problems. We'll take a look at how to apply Newton's laws in this week. I'd also like to start on torque or moment or the moment of force. And of course, we'll be working on these things with the practice problems. We will also go through some hints and tips for you guys for the test. Okay, so what is force? Now, in our case, we're talking about force in terms of a push or a pull. And when we're looking at a force as a downward extension, like this structure here, we need to be able to calculate how this is going to react. And we've got forces that are acting because of gravity. We've also got forces that are acting because of wind. We've got inertial forces or loads from earthquakes as well. And a lot of what we study or the work that we do is based on Newton's laws. So Newton's first law is that that any body will remain at rest or in motion unless acted upon by an exterior force or an external force or resultant of a force. So basically, this is sort of summed up as the law of inertia, that matter likes to continue in its state of rest or uniform motion unless there's a force acting upon it. Now, the rate of change of momentum, well, so momentum is equal to the velocity times the mass, and the rate of change or the acceleration is directly proportional to the force that's acting upon it, and that's where you get the equation F is equal to ma, one of the more famous equations in physics. The third law is that for every action, there is an equal and opposite reaction along the same line. So this is something I'd like to pinpoint a little more clearly before we move on. So let's say for our practical purposes, let's say you've got a body, a box, let's say, it's acting in a downward direction. Why? Because of its weight, the force of weight. What Newton's law is saying is that you will get a force equal and opposite acting in an upward direction because the surface that this box is resting on is going to push back. This is also known as the normal force. This is also known as the normal force, okay? And basically what you can do is you can look at all these forces that are having um, these actions upon the structures that you're designing. So let's say you've got a bunch of snow that's sitting on top of your roof, and it's acting in this direction, the center of the body of the snow, or maybe it's something else. Maybe it's just a person, 300-pound person. With this angle and with the information given, you can determine what are all the forces acting, what are the moments of forces acting on this entire structure. And that's where we want to get to as we move forward in the course. Now, we've already discussed how vectors have both magnitude and direction, and you want to combine them with the rules of addition, right? So let's just go over that, what I would want you to focus on when it comes to the rules of addition for vectors. What do I mean by that? So let's say you've got vectors acting F1, F2, F3, and F4. Basically, in order for us to add all of these vectors that are adding, first you want to get all of the x components, and then you want to get all of the y components. You want to find F1x, F2x, F3x, and F4x. And then you want to get F1y, F2y, F3y, F4y. And then you just add all of these, and then you add all of these. Now, another thing I want to point out to you guys is that when you look at the x components, be very, very careful. If the x component is in this direction, it is negative. If the x component is in this direction, it is positive. If the y component is in this direction, positive. If the y component is in this direction, negative. They're very important because if you get this wrong in your addition or subtraction, your final answer will be way off. And I think you might remember last week in one of our practice questions, I think we made that mistake and that caused us to have a significant error. I like to use the triangle rule. You're welcome to use whichever method suits you. But the reason why I teach the triangle rule or the triangle method is I find it to be the easiest and the simplest. Okay, now it's important also to understand the line of action of the force is the direction, and the line along which this force is going to be acting. Here again, the line of action of force. This is going to give you the ability to know what the angle is with the vertical or the horizontal in order for us to understand what the components are. Now, the magnitude is basically the quantity of the force, and we use pounds, or we show it as a pound number, or kips, or kilopounds. That's 1 kip, or 1 K is 1,000 pounds. So in this case, this is kilonewtons, so no need to worry about that. So the direction of the force is defined by the line of its action and sense, right? So this is the sense, that's the direction. This is the line of action, and the angle gives you the direction. In this case, 50 degrees would be the angle to the horizontal, whereas 40 degrees is the angle to the vertical. Now, in statics, or in this type of study, when we're looking at different bodies, we're assuming them to be rigid, meaning that there's not going to be any deformation. Okay, so if 1 kilonewtons of force is applied on this structure, we are assuming that there's no deformation taking place. There's no change in the shape. Now, this is not our area, meaning if we have a structure that deforms, that is not the area of this course. This course is about statics, and it's going to assume rigid bodies. Strength of materials is where you get into the study of deformable materials. Another aspect of this part of the course is that you can actually transmit the force in your structure. So let's say you've got your weight, it's actually acting in a downward direction. You can actually transfer it in your calculations down to here, as long as you've got the same line of action. Another thing I wanted to show you guys is that the reactionary force here, or R, is the normal force from the Earth. That's the reactionary force to the weight. Now, if you've got all the forces acting in one line, that's called collinear. If you've got all the forces acting along one plane, which is mostly what we're working on right now, we're just doing coplanar forces. And if they're parallel, this is how they're depicted. Here you've got these 3 forces. They're coplanar, they're concurrent, they're acting in the same location. Here you've got non-coplanar. They're parallel though. They're acting in this. They're in this along the same direction. Well, they're parallel to each other. Some are upward. Some are, one of them is downward. And here you've got non-coplanar, but they're concurrent. They're acting at the same location. And when it gets quite complex when you're looking at forces that are not in the same plane and they're not acting in the same point. So the process of adding vectors is to get the net force, the resultant. So we need to understand how we're going to do this. So in this case, let's say A is the first force, it's 15 kilopounds, and B is the second force, 17K, and you've got the angle shown. Now, very, very important here. If you're given the slope, you should still be able to determine that angle. So we've got A, which is this force, which is equal to 15K. The only information we're given is the slope is 3/4. So how do you determine the angle? Well, we can find this angle because it's going to be the same as this angle by using this. So in this case, theta, so tangent of theta will be equal to 3/4, meaning theta is equal to, let me go ahead and calculate that. Meaning this angle is 36.87 degrees. That's what that information is, rise over run. And then what you would do is you would then determine AX and AY using the angle. Okay. Now, something that some people will like to do, others might not, is when you're performing such work, let's say you've got all these vectors acting. And you're trying to add all three of them. What I like to do is I like to draw FC separately, and then FA separately, and then FB separately, and then determine their components separately. That way, I reduce the risk of making too many errors. In my calculations. And I will show you what I mean by that. Once I've calculated the X component and the Y component, I should be able to determine a resultant. And that's what's being shown here, the resultant. But in order to get the correct answer, I need to have a magnitude of the resultant and direction. And we'll show you how that is done. Now, as I said earlier, you can use the parallelogram, and these notes sort of show how that is. I like to use the triangular method, the tip to toe, to show it graphically on how I'm performing my addition. And as you can see, here's the tail, and here is the tip to tail, and showing them being added. But for all practical purposes, when we're performing the actual uh, arithmetic portion, you do need to have the components calculated. So now is probably a good time to see how this is done. Give me a second here. Just in case when I'm showing this to you, maybe it'll be a little bit easier. You watch somebody else.
I didn't know. In this video, we're going to talk about.
And this will give you an insight into what we're going to be practicing. Let me know if you don't hear the sound.
How to add vectors. So a vector is a quantity that
You guys
has
all hear the sound?
magnitude.
Yes.
Oh, okay, good. Thank you. You, Josh.
And direction. So let's say if we have a force vector that's 100 newtons directed towards the east. The magnitude is the size of the force. It's 100 newtons. And the direction is east. And let's say if we want to add it to another force that's directed east as well. And let's say it's 50 newtons. So the resultant sum of these two forces is going to give us a net force of 150. Whenever you have two vectors that are parallel to each other, you can simply add the numbers to get the resultant sum. Now let's say if we have a 200 Newton vector directed east and a 120 Newton vector directed west. What is the resultant vector, and also specify the direction? So this is positive 200 because it's directed towards the right. This is negative 120 because it's directed towards the left. If you add these two, you should get a net force of positive 80. Now it's going to be smaller than the original one, but it's still directed east because this vector is greater than this one. Now here's another example. Let's say if we have a force vector that's 60 newtons directed east and another one that's 90 newtons directed west. What is the resultant force vector? And what's the direction? So this is positive 60, that's negative 90. So we're going to have a net force of negative 30 newtons. Or you could just say 30 newtons directed west. Now, what if we have a force that's 80 newtons directed north and another one that's 120 directed south? So 120 minus 80 is 40. So the net force is going to be 40 directed south. And if you recall, this is north, south, east, west. Now sometimes you may need to add two vectors that are not parallel or anti-parallel to each other. So let's say if we have a 30 Newton force vector directed east and a 40 Newton force vector directed north. What is the resultant force vector? If you have two vectors that are perpendicular to each other, you could find the resultant force vector by finding the length of the hypotenuse of the right triangle that is formed. So therefore, the resultant force vector is going to be the square root of F1 squared plus F2 squared. Let's call this F1 and this force F2.
So this is quite important what's being described now. Once you get the components of the resultant, this is how you get the magnitude of the resultant.
So it's going to be the square root of 30 squared plus 40 squared. If you're familiar with the 3, 4, 5 triangle, then this is going to be the 30, 40, 50 triangle. So the resultant force is going to be 50 newtons. Now sometimes, in addition to finding the magnitude of the resultant force vector, which is 50, you may need to find the direction as well. So you got to find the angle theta. To find it, you can use this formula. It's the inverse tangent of the y component divided by the x component. So the force in the y direction is 40, and the x direction is 30. So to find the angle, it's going to be arctangent the opposite side, which is the y value of 40, over the adjacent side, which is the x value of 30. Hopefully you're familiar with SOHCAHTOA. Sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite relative to theta over the adjacent side. The arctangent of 40 over 30 is 53.1 degrees. So we can say that the resultant force vector has a magnitude of 50 newtons and a direction of 53.1 degrees relative to the x-axis. Let's try another example. So let's say if we have a force vector that's 50 newtons directed west and another one that's 120 newtons directed south. Calculate the magnitude of the resultant force vector and find the direction. So let's draw a triangle. So this side is 50 and this side is going to be 120. So the resultant force vector is the hypotenuse of this triangle. So notice that it's in quadrant 3. Now, if you're familiar with the 5, 12, 13 triangle, then the hypotenuse has to be 130. So the resultant force vector is going to be the square root of 50 squared plus 120 squared, and that's going to turn out to be 130 newtons. So that's the magnitude of the resultant force vector. Now all we need to do is find the angle. So first, let's find a reference angle. To find a reference angle, use the arctangent formula take the force in the y direction, divided by that in the x direction, but make it positive initially. This will give you an acute angle between 0 and 90, and then you could adjust it later. So arctan 120 over 50 will give you a reference angle of 67.4. So here's the reference angle. It's inside the triangle. Now what we need is the angle relative to the positive x-axis. So if this is 180, then the resultant vector is 180 plus 67.4 relative to the x-axis. So it's at an angle.
I would actually report this as 67.4 degrees from the horizontal. I wouldn't get into this complication.
Angle of 247.4. So therefore, this is the resultant force vector, which has a magnitude of 130, but an angle of
Something weird was happening there.
.4 degrees. So that's the answer. Now let's say if we have a force vector of 45 newtons directed east, and we wish to add it to a force vector of 60 newtons directed south. Find the magnitude of the resultant force vector and also the angle. So let's draw a triangle. So this is 45 and this is 60. So let's find the magnitude of the resultant force vector. So it's going to be the square root of 45 squared plus 60 squared. Which is 75 newtons. So that's the magnitude. Now we got to find the angle. But let's find a reference angle first. So it's going to be arctangent, the force in the y direction, divided by the force in the x direction. So that's 60 over 45. Which is 53.1. Now that's the reference angle. The first force vector is positive. It's directed east. The second one is directed south. So therefore, the resultant force vector is in quadrant 4. Now, if this angle is 53.1, to find the angle relative to the positive x-axis, it's going to be 360 minus 53.1. Keep in mind, a full circle is 360, but you need to go back 53.1 degrees. So 360 minus 53.1 will give us an angle of 306.9. So the resultant force vector has a magnitude of 75 newtons, and it's directed at an angle of 306.9 degrees relative to the positive x-axis. So this is the answer. So if you know the resultant force vector is going to be in quadrant 1, then the angle is going to be the same as the reference angle. And keep in mind, the reference angle can be calculated by taking the inverse tangent of the force in the y direction divided by the force in the x direction. And if you always make these positive, you're always going to get an acute angle between 0 and 90, which is the reference angle. Now, if you know the resultant force vector is in quadrant 2, then to find that angle, it's going to be 180 minus the reference angle. If it's in quadrant 3, we covered this one already, it's 180 plus the reference angle. And if you get an answer that's in quadrant 4, it's going to be 360 minus the reference angle, which was the case in the last example. So it's helpful to know these things, or you could just see what to do visually once you graph everything.
So that part I wouldn't
Now,
actually agree with him. I like to look at the things a little simple, more simple, but let's just continue with this person.
sometimes you may need to add vectors that are not parallel or
Now, this next portion is quite key. Let's see how this person approaches it.
perpendicular to each other. So let's say if we want to add this vector, which is 100 newtons directed east, plus another vector, let's say it has a magnitude of 150, but it's directed at 30 degrees above the x-axis. How can we find the resultant vector? First, let's relist what we have. The first vector has a force of 100 newtons, and its angle, it's east, so it's on the x-axis, so it has an angle of 0 degrees. The second force vector has a magnitude of 150 newtons, and it has an angle of 30 degrees relative to the x-axis. Now, what you want to do is you want to add these vectors using the component method. So you want to break these forces into their components, add their respective x and y components, and then you could find the resultant force vector. So let's say if this is a force vector, this is the x component, and this is the y component. And here is the angle. F of x is equal to f cosine theta, and f of y is f sine theta. F, you can find it by using Pythagorean theorem. It's f of x squared plus f of y squared. And the angle theta is the arctangent of f of y divided by f of x. So those are some formulas that you're going to find useful in this portion of the video.
So this is basically the core of what you'll be using to add vectors in that are not exactly parallel.
So what we need to do is find f1x and f1y. So f1x is going to be 100 cosine of 0. Cosine of 0 is 1, so 100 times 1 is simply 100. f1y is going to be 100 sine of 0. Sine of 0 is 0. 100 times 0 is going to be 0. Now, let's do the same for f2x and f2y. f2x is 150 times cosine of 30 degrees. Now, if you type that in your calculator, make sure it's in degree mode. So this will give you, as a decimal, 129.9 newtons. f2y, that's going to be 150 times sine 30, which is just 75. Now, what we need to do is add up the x components. So if we add those two values, the sum of the forces in the x direction is going to be 100 plus 129.9. So that's going to be 229.9. And then we need to find the sum of the forces in the y direction, which is just 0 plus 75, so that's simply 75. So f of x is 229.9 newtons, and f of y is simply 75 newtons. Now let's go ahead and draw these values on an xy plane. So f of x is 229, and f of y is 75. The resultant force vector is the hypotenuse. And to find it, it's going to be the square root of f of x squared plus f of y squared. So you should get 241.8. So that's the resultant force vector. That's the magnitude of it. Now that we have the magnitude, we need to find the angle. So it's going to be arctangent f of y, which is 75, divided by f of x, which is 229.9. So the angle, which is already in quadrant 1, is 18.1 degrees. So now we have the magnitude and the direction of the resultant force vector.
There's nothing more powerful than you making your thing happen.
Okay, so that was a decent video, I thought, describing what we're trying to achieve here. Now let's take a look at this question. So this is the question, right? So what I would suggest in this situation is split it up into its three different vectors and work on each separately. So let's go ahead and do that. I'm gonna switch mine to make it easier for me. Okay, so let's go ahead and do that. So the first of these is F1. F1 is equal to 10K, and we already know the angle, given us 30 degrees. So let's say this is F1x and F1y. So sine 30 degrees is equal to F1x over 10K. Therefore, F1x is equal to 10K times sine 30, which is equal to, let's go ahead and calculate that. 30 sine times 10 is equal to 5K. The next thing I wanted to point out is it's in this direction, so it's positive. So we've got our first x component. F1x is equal to 5K. Now F1y is going to be equal to 10K multiplied by cosine 30, which is, let's see, cosine 30 times 10K is equal to 8.66. 8.66K. And it's in an upward direction, so it will be positive. 8.66K. All right. Now let's focus on F2. F2 is equal to 12K. But here's where I want to point something out. Since it's in this direction, I would put a minus. Secondly, I would point out that this is equal to F2x, right? Because it's along the x-axis. Do we have F2y? Yes, we do, but it's 0. So that ends the discussion on that. And we can then add that to this. F2x is equal to minus 12K, and F2y is equal to 0. The reason why I like to keep it in one spot is then I don't lose it, and hopefully I don't make a mistake. Okay, let's go ahead and erase all of this and focus on the third vector. So the third vector has an interesting scenario. 18k is equal to f3. This is f3x, f3y. We also know that the slope is 1 to 1. Therefore, to calculate this angle, so we're going to calculate this angle, the inverse tan of 1 is equal to theta, which is equal to 45 degrees. Okay. Now, using this, f3x is equal to f3, which is 18k times sine 45 degrees, which is equal to, so let's go ahead and calculate that. 45 sine times 18 is equal to 12.73k, and it's in this direction, so we'll leave it as a positive. And f2x, or f3y is equal to 18k cosine 45 degrees, which is equal to, what is it equal to? 45 cosine times 18, it's the exact same thing, 12.73k, but it's in a downward direction, so I'm going to put a minus here. Okay, so now I'm going to need your help here. Why am I going to need your help? Because I erased, it looks like I erased some of the information. So I've got f3x is 12.73, f3y is minus 12.73. You know, f2y is equal to 0, and f2x is equal to minus 12k. Can somebody tell me what f1x is and what f1y is? Can somebody tell me that in the chat, maybe? Hopefully you guys were making notes. If you don't, I'll just have to look it up here. F1y is 8.66k and f1x is equal to 5k. So now that you have all of this information, what do you do? What do you do? You add f1x plus f2x plus f3x. And then for fry, the resultant y, f1y plus f2y plus f3y. All right, so please go ahead and try to solve that. And let's see what you guys get. We'll give you a few minutes to try to solve that. Yeah, I haven't heard anything from anyone, so I guess either you didn't try to solve it or you're, you are unable to solve it for some reason. So let me show you. So Rx is going to be, so F1x is 5k minus 12k plus 12.73k, which is going to be equal to, thank you, Tammy. I think you might be right. So 5 minus 12 plus 12.7. So I'm getting 5.7k. And Ry, I'm getting, it's going to be 8.66 plus 0 minus 12.73k. So 12.73 minus 8.66 is equal to 4 minus 4.07k. Now, this one, just make sure you don't make that mistake. Yeah, I agree with you guys. Now that I know that Rx, so the X component of the resultant is 5.7, well, it should actually be 5.73k, and Ry is minus 4.07k. So I'm going to show you guys what I would do next in this situation. So at this stage, now I'm going to stop. I'm going to take a look at the X and the Y component of my resultant. And I know, based on what I have, that this is what it's going to look like. So 5.73k. I know it's going to look like this. Why? Because it's a positive. And Ry minus 4.07k. This is what our actual resultant will look like. Now, number one, what's the magnitude? So R square is equal to 5.73 square k squared plus minus 4.07k squared. So let's go ahead and solve this. 5.73 times is equal to 32.83 k squared plus 4.07 times is equal to 16.56 k squared. This is equal to plus 32.83, 49.39 k squared. So R is equal to 49.39 k squared is equal to, should be 7 something, 7.03 k. That's the answer, but is that the complete answer? Absolutely not. You need to get at least one of these angles. So I'm going to look for this angle. So tangent of theta is equal to, what is it equal to? We're just going to use this 4.07 over 5.73. So therefore, theta is equal to, go ahead and calculate that, 4.07 divided by 5.73, arctangent, 35.38 degrees. And that basically gets you to where you need to be in order to complete the solution. So let's take a look at the solution from the book. Sometimes I find that the actual solution from the book actually it looks more complicated. It's actually not that complicated, but I mean, that's just the way certain books are written. So here you go. You're seeing this. They solve for F1y and F1x. We did the same thing. They also figured out the components for F2. You notice there's only F2x. Then they did the same for F3, which is what we did. And then they added all the X components. That's what's showing here. And they added all the Y components. That's what's showing here. And then they drew it. So I drew it a little bit differently, but essentially it's the same and we get the same result. Okay, 35.4 degrees from the horizontal. Okay, and you can apply the same principles no matter where, no matter what situation you're in. And that's what we're going to try to see here. So let's say you've got a weight that's sitting on this slope. The weight is 300 pounds. So you're going to have a component of this along the surface of this. That's your X component, and one that's perpendicular. And that's what you calculate. It doesn't matter what the scenario is. You can calculate the X and the Y component of this weight by using the angle. Another interesting aspect is the resultant reaction that you can also calculate from the Earth. So let me go back and try to help you guys understand what that means. So you've got a structure and you've got a foundation. So you've got a structure here. Whenever you see a weight acting in a downward direction, you might see drawings showing the reaction. That's the normal force when you see a slash like this. See, that's the foundation. Say this is the ground surface. All right. It's the weight. Now let's switch that situation. Flip that situation. Let's say you're on a curved surface. This is the weight. So the weight is technically acting in this direction. But you can actually show the Y component like this. Let's say this is a weight Y, weight X. Okay, this is going to come in handy. And the normal reaction from the surface, so the normal force would be like this. And you'd use this angle to calculate the X and Y components of the force of weight. Okay. What I want to do is I want to show you how in a certain situation you can actually use what we know to determine what the reactionary force is going to be from the subsurface, from the Earth. So let's take a look at something here. So here we go. We've got this two forces acting at point A, and they're F1 and F2, and we've got a resultant force. So what you can do is first determine the X and Y components of the force F2. Then we know that this is a static structure. That means that the sum of the forces in all directions are zero. Therefore, Rx is equal to zero. So whatever you get as F2x should be equal to F1. So that's one equation. And F2 cosine theta is equal to F1. Why? Because that's what we got in the equation. Therefore, you can calculate F2 as 7 kilonewtons. Okay. Now, before we move forward, I think it's a good time to take a short break. And then we'll come back and wrap up our discussion on sums of forces to understand how to make certain calculations. Okay, so we'll meet in a few minutes. Let's take a short break, 5 minutes or so. Any questions at this point? Are you guys going to be able to run these calculations in the tests? That is a lot of what we're looking at. Okay, another thing I wanted to mention here is that when you have certain situations or you have calculations, always remember that the sum of the forces and later on the moment of forces is equal to 0. That is the main principle in statics. Because if there was a resultant force, you would not be able to, the structure would not be able to stand. So when you're using this, it should be able to help you. So if you got a bunch of forces in a certain direction, the sum of the vertical and horizontal components should remain 0. Now let's try to emphasize that with this short video here. That should help you understand this.
Air technicians are experts at heating, cooling, water heating, and water purification. We can help you with a range of affordable solutions to help your home run smoothly.
Enercare, experts at home.
25 years of innovating has led to today.
Can you let
Today,
me
your
know if
EV
you're seeing
inspires your adventures.
and hearing
Get
the
in a
video?
Kia Niro EV and see what tomorrow brings.
Kia, movement that inspires.
I can see and hear just
Okay,
fine.
in today's video,
Pardon me?
Yeah, I can see and hear just fine.
Okay, thank you.
we're going to be talking about equilibrium applications of Newton's laws of motion. So, what is equilibrium? An object is in equilibrium if it has no acceleration. In other words, it's not moving or moving with a constant velocity. In that case, all the forces in the x have to equal 0, and all the forces in the y have to equal 0. This is very similar to our vector addition lab we did at the beginning of the year. All the force in the x added to 0, all the force in the y added to 0, because the object wasn't moving. And remember, the object could be moving with a constant velocity and still be in equilibrium. Okay, so let's think about how we would solve these type of problems. The object or objects in which equilibrium are to be applied are selected. In other words, what is the object you're going to be looking at, or objects you're going to be looking at? And then you draw a free body diagram for each of them. And you include, obviously, only the forces acting on the object, not forces the object puts on its environment. And you choose a convenient coordinate system and resolve all the vectors into their components, the x and y axes. Then you use Newton's laws and equations to solve for any unknown quantities. So it's pretty straightforward. So we're going to give it a shot with this problem here. Okay, so you got some guy's leg in traction. The tension, this is free to move, this is free to move, and this weight holding down is pulling on his leg, both T1 and T2. And what we're looking for is we would like to find out what the force in T1 is, the tension, excuse me, in T1 and T2 is, and also what this force here is. Okay, so we have the object, which is basically the center of this, and there's three forces acting on it. One pulling back this way, one pulling this way, and one pulling this way. So we're going to draw a free body diagram. Here's our free body diagram. We represented this center position just by a dot, and we have a force acting backwards, T1 pulling up into the right, and T2 pulling down into the right. And we broke this into x and y components. I found that the idea of thinking of it along the axis of F been calling that the x-axis would be the simplest, and then I created a y-axis perpendicular to that. So that allows me to break this tension into its components, its x and y components, as well as this tension into its x and y components. So if we took this vector, we broke it into how much is in the x and how much is in the y. Okay, so if you're looking at this angle right here, this would be T1 cosine of the angle, and this would be T2 sine of the angle. Normally I like to draw it over here, but they drew it here for this demonstration. And we did the same thing down here. All right, so now we have a free body diagram, and we've resolved it into components. Now we need to determine what all the forces in the y equal. Well, it's an equilibrium, so it has to equal 0. So we have T1 sine of 35 minus T2 sine of 35 equals 0. And let's see where this came from. You have T1 sine of 35 acting upwards. There you go, it's acting upwards, pulling up. At the same time, this is pulling down. So that's why this one's positive and this one's negative. And in the x direction, it's still equal to 0 because it's not moving. And here we have T1 cosine of 35 pulling to the right and T2 cosine of 35 pulling to the right with F pulling to the left, so it's negative. And we try to solve for unknowns. So we take our first equation and realize that sine of 35 and sine of 35 are in all terms, so we can get rid of that. And we term T1 minus T2, 0. And we know that T2 has to equal the weight that's hanging down on it, causing this tension, right? So T2 is equal to 2 kilograms times 9.8 or 21.6 newtons. So that means that T1 is equal to T2, which is equal to 21.6 newtons. Now to find out what's happening with F, we have to use the x equation because F is only in the x equation. All right? Once again, we could divide both sides by, well, we can't actually divide by 35, can we? Because there's this term F doesn't have a cosine of 35 in it. But we do know that T1 and T2 are equal to each other. And why are they equal to each other? Because these two angles are equal. And not all problems will they be equal. You'll see that in the next problem we'll cover. So that we know that we could replace one of the T's with, we could replace T1 with T2 because basically they're the same thing. So 2T2 cosine of 35 equals F, or F is equal to 35.3 newtons. And that's a very simple application of equilibrium problems, static equilibrium problems. Let's look at something that's a little bit more complex. Okay, you got a guy trying to put an engine block into a car that's being held up by a pulley up here. And obviously this tension is probably taking most of the weight, I would think, just looking at it. And he's pulling it out to the right, trying to position it correctly. All right, so we have to draw our free body diagrams. T1 is acting that way, has a component in the y, T1 cosine of 10, and in the x, T1 sine of 10. Now, it's interesting to notice that a lot of people always think that the y direction will be sine and the x direction will be cosine, but it all depends on what angle they give you. In this case, they gave us this angle. So the x is actually the x direction is actually sine, and the y direction is cosine. And we resolve this vector into its components as well. We have T2 sine of 80 and T2 cosine of 80. Now if you're having a difficulty understanding this, take a moment, pause the video, look at it, and determine where these vectors are coming from and where these components are coming from. And obviously we still have weight acting down. So we have T1, T2, both broken into components, and weight acting in the y. So we could summarize this. Okay. So T1 has an X and Y component. T2 has an X and Y component. And weight only has a Y component. And by the way, that weight is 3,150 newtons. Okay. Now let's see if we can come up with some equations for this. Okay, in the X direction, we have negative T1 sine of 10 degrees, because it's pulling to the left. Positive T2 sine of 80, because it's pulling to the right. All that must be equal to 0. And then we have in the Y direction, we have our T1 cosine of 10 degrees pulling up, our negative T2 cosine of 80 pulling down. That's why it's pulling down, so it's negative. And weight is obviously negative. All right, so we actually have two equations and two unknowns. So we're going to have to solve them simultaneously. So the first equation, the one up here, I'm going to solve for T1. And T1 ends up equaling to this quantity here. Okay? If you need a moment to figure out how I did that, pause the video and look. Okay? And now I'm going to be able to take that equation and substitute into the second. So wherever there was a T1 in the second equation, I'm going to put all this stuff. Okay? So I took all this stuff and put it in for T1. Now I only have T2s and weight, which I know. Now I'm able to solve for T2. And when I do that, I end up with 582 newtons. And you can confirm that on your own as well. Okay, now that I have one of the tensions, I'm able to calculate the other tension. And I just have to go back now into the first equation, or any of the equations actually, and plug in what T2 is, and now I'm able to figure out what T1 is. Okay? And this is just algebra, so if you need a moment to look at it, once again, pause the video, see where I came up with these equations, how I manipulated the algebra to come up with an answer of 3,300 newtons. And that's basically how you do equilibrium problems using Newton's laws. Basically, to summarize it, what you're doing is you're picking the object you're looking at, you're drawing free body diagrams out of it, you're breaking any vectors into the components, and then you're solving for any unknowns. And sometimes you have to solve simultaneous equations.
Okay. So now let us move on to our next main item. So we're going to start talking a little bit about torque. This is the next main item for the course. It's torque. And essentially, it's using force, but around an axis. So what you're trying to do is you're trying to move an item around an axis using force. And you can see based on the images that this is how a lot of our tools are working. So torque, it's also known as moment. It's also known as the moment of the force. So let me try to sketch that or talk about that a little more here. So if you've got a force and it's acting in this direction, but it's pushing something like a lever or a door around this axis, it is now generating a moment of force. So if this is the force and this is the distance of what is this distance? the perpendicular distance to the axis of rotation. That force, so let's say this is this distance. So torque would then be calculated by F multiplied by D. Okay, this would be in meters, in newtons. So what would this be in Newton meters? This is also, so this is known as torque. It's also known as moment or the moment of the force. Very, very key concept that you're going to be learning and applying in the next phase of your course. This really is important because a lot of what you're going to be seeing in the future in your calculations is how weight is transferred to the load-bearing formation of walls. So let's just take a look at this. You've got a door, and when you're calculating or determining the line of action of the force, remember that if you were to apply the force to the doorway, just imagine you're in the roof or from the vantage point of the roof. If you push the door in this direction, you get zero torque. Why? Because the distance between the line of action of the force and the axis of rotation is zero. So that's no good. If you were to push the door in the direction of FC shown here, you do get some torque, but maybe not the maximum. However, if you were to push, because look at this, the line of action is not going to be from, or the distance to the line of action is not going to be from here to here. It's going to be from here to the perpendicular distance of the line of action of the force. But if you were to push this door, as FA is showing here, it's the maximum line of action of the force. And that's how our arms work, using torques to lift things. And you can use this animation here to understand how torque is. It's the perpendicular distance of the line of action to the force multiplied by the magnitude of the force is the torque. So this part I don't think we need to spend too much time on, because now you should have a good understanding of this portion of the course or this information. So what is moment? You've got two axes of rotation here. The line of action of the force is given here. So I would say that from this axis of rotation, this will be the perpendicular distance. And from this line of action of force, it's going to be this. So if we're going to calculate the moment of the force, how are we going to do that? Well, we need to understand the direction of the motion of the force, the perpendicular distance, and also the direction. Clockwise moment of force is always shown in a negative. Anti-clockwise moment of force is always shown as a positive. Here's the calculation. Moment is equal to the perpendicular distance multiplied by the force. What is this perpendicular distance? It's the perpendicular distance from the line of the force, line of action of the force, to the axis of rotation. So here you've got force around M1, the distance is D1. So F1, F is going to be F times D1, that's a moment around M1. And it is counterclockwise, so it's positive. D2 is going to be F times the distance D2, or the moment around M2 is going to be F times D2. You can see these animations are sort of showing what it means. You've got the axis around which this moment is occurring. But the key thing to find is the perpendicular distance. and the line of action of your force. This gets complicated, especially when you're working in 3 dimensions, which we're not going to, at least not for a while. But let's say got a moment of force around. Oh, that's the line of action of the force, and that's the perpendicular distance. And because of the way it's rotating around this axis, it's going to be clockwise, meaning it's negative. It can also be written using the x and y components of the force. And sometimes that is a lot simpler. So we're going to illustrate this by one practice question. And that will be the end of today's lecture. And then we'll talk about your test a little bit. So you've got a large piece of wood. It's a beam, it's weighing 800 newtons, and it's supported by 2 posts. Okay, so there's a couple of things before we move on I want to point out. So when you have a regular shape, what do I mean by regular shape? Triangle, in this case a beam. Where are you going to show the line of action of the force of the weight? From the center. And it's pretty easy to determine where the center is in this scenario. Where it gets complicated is if you've got a regular shape. Where's the line of center? You are going to calculate that. Or let's say you've got a structure. Got all these different pieces at it. I'm just showing it like a child's drawing here, but let's say you've got a structure, all these things coming together. You need to be able to determine where the line of action of the weight is. But at this stage, it's not a big problem for you. Why? Because we're just going to be dealing likely with regular shapes. So be careful as you go along, understanding how you draw the sketch, understanding the dimensions, distances, understanding density and how it's going to be applied for your material, understanding the line of action of your forces, the direction of the moment. It's going to be key. Always remember, clockwise moment, clockwise is negative. Counterclockwise is positive. What does that mean? If you've got this door and you're pushing the door this way, right? And this is the axis rotation. So this is what? Clockwise. That means this is going to be negative. If you were to push the door in the opposite direction, right? Like if you were to push the door, I'll draw it with a different color here. Maybe I'll use green. If you were to push it in this direction, then it would be this way. And that would be positive. Why? Because it's counterclockwise. Is that clear? This is going to come into play in the future. Is that clear?
Oh, yeah.
This is going to be really important in the future modules. Are you guys also clear on the fact that I'm only here for a couple more weeks? I will not even be in the country after that. So make sure that you are aware of the habits, the methods, the way the new professor is going to want to run the course. And as I had mentioned, I hope I mentioned to you guys, I'm hoping to have him or her visit our classroom. All right, let's go back to the question. So this is the practice question. A large wood beam weighing 800 newtons is supported by 2 posts So there's going to be a diagram showing this. If an unthinking man weighing 700 newtons were to walk on the overhang portion of the beam, how far can he go from point A before the beam tips over? So you're going to use the principles that we've just been talking about. So you've got the beam, and you've got its weight right from the center, line of action, it's 800 newtons, and we know that it's in the middle, and we know that it's 4 meters, so this is going to be 2 meters. What else do we know? Okay, so this is given in the question. So this distance is 1 meter, this distance is also going to be 1 meter then. And this man is walking a distance x from this post. So these are the posts that keep up this beam. There's post A and post B is not labeled. I guess it's not relevant in this calculation. So there's two forces. And you're going to be able to calculate the moments around A using these two forces. So 800 is going to be in a what? Counterclockwise direction. 800 newtons, so that's going to be positive. But we need to know the distance. I think that's 1 meter. 700 newtons is going to be in a clockwise direction. We don't know the distance, it's x. So that's going to be interesting. So it's going to be 800 times 1 minus 700 times x, and the sum of the moment should be equal to 0, so that there's no resultant moment. And there you go. That's the equation written, and you can easily solve for x. It's 1.10 meters. All right. We're going to leave this for now. We'll talk about this, some more examples on moments of force next week. Right now, I'd like you guys to simply focus on your test next week. So do you guys remember what I mentioned about the timings? Guys remember what I mentioned about the timings? Okay. Well, Risa, if you missed the last class, did you not watch the recording? So the two options for the online test are 4 p.m. and 7 p.m. So that will be test version 1, test version 2. I would like you guys to attend like you are now, so with your cameras on. Also, what I'd like you guys to do is create your formula sheet, create your own formula sheet, and to basically write your test and upload it once done. You can scan it using your cell phone and then upload it. There'll be a link. So it'll be 4 p.m. or 7 p.m. on Wednesday next week. So just log in like you do for this. Oh, 3 p.m. Sorry. Yeah, sure. My apologies. Not 4 p.m., 3 p.m. Good catch. Okay. And if these don't work, contact me. I also have one additional option, but that's going to be earlier on in the week. It'll be Monday at 11 a.m. I'm not. I'm going to be occupied because it'll be in person, and so I'm not encouraging that. These are the two times that I'm asking. Okay. If you want to do Monday, I'm not going to be able to answer many of your questions because I'll be in class, but I will allow you to write it. So that would be version 1A. So I'm not encouraging that, but I know one or two of you have requested that. Okay. No, you don't have to upload the formula sheet. It's not necessary. All right. Now, what do I want you guys to be aware of? There'll be 5 questions. One question is from units and conversions. 4 questions are from the vector portion. So the 4 questions are going to be similar to your assignment 1. 1 question is going to be similar to assignment 2. 1 question is going to be assignment 1 and 4 questions like assignment 2. You'll have an hour and a half to complete. And just don't use any solved examples in your formula sheet notes. But based on what I've seen in the past is don't forget to put a unit for your answer. It'll make life easier for you if you sketch. If you give me an angle of the vector without context, it is still incorrect. So make sure you give me the context. You've seen how I prefer the triangle method, but you can use whatever method you want as long as I get the correct answer. Okay. One thing is requested, scan as one PDF file when to upload, and please circle or show me where your answer is. Sometimes I can't find it. And the reason why I insist on one PDF file, it's just really hard to open multiple pages to make sure that I keep track of everything. Also, if you send in the answer as a Word document, it tends to distort it. And sometimes I can't read the answer. And then it just creates a bunch of confusion. Okay. So that is what I wanted to talk about regarding the test. Any questions? How many questions in total? 5. 5 questions in total. Okay, I'm going to turn this off now, the recording, so that it's hopefully available soon after our time is